look closely at how the physical and digital worlds actually operate. From the sprawling reach of social media platforms to branching molecular structures or the cascading links in a global supply chain, data rarely exists in isolation. It lives in a messy, interconnected web. But standard machine learning models aren't built to read the world that way. They expect information to be served up in perfectly clean, isolated tables of rows and columns. When you take a complex network and force it into a rigid spreadsheet format, you destroy the most vital pieces of information. You are quite literally snapping the connecting lines, losing the context of how all those different pieces interact. A traditional neural network might be excellent at evaluating a single, isolated bank account or an individual buyer. However, it remains blind to how that account behaves within a wider financial ring or how that buyer influences their local market. To process reality as it actually exists, we use an architecture designed for the task, graph neural networks, or GNNs. These models are engineered to capture both the individual traits of an entity and the structural web connecting it to everything else. Predicting the outcomes of global systems depends on mapping these hidden influences. Accuracy at scale depends on an architecture that can calculate how one event cascades through 1,000 others. To understand how a GNN maps these relationships, we start with a specific vocabulary. The individual entities, like a person or a server, are called nodes. The lines that connect them are the edges. We translate this visual map into a language the machine can read, using an adjacency matrix. This gives us a strict mathematical grid, where a 1 indicates a connection between two nodes, and a 0 means no connection. But the real power of a GNN comes from zooming in to see how a single node actually learns from its surroundings. It starts with message creation. Our central node receives encoded feature data from its neighbors. Then comes aggregation and update. The node combines these messages. Its internal array physically expands, calculating a richer representation of itself based on the company it keeps. This process repeats layer by layer. In the first layer, the node learns about its immediate neighbors. In the next layer, it learns about the neighbors of its neighbors, continuously expanding its receptive field across the network. Through this iterative communication, a point of data that started completely isolated is transformed into a context-aware entity. It now holds enough structural intelligence to drive advanced predictive logic. Because network structures vary wildly across different industries, engineers use different architectures, acting as distinct dialects to solve specific scaling and logic problems. Graph convolutional networks, or GCNs, serve as a solid baseline. They function by gathering and smoothing out an aggregated representation of a node's neighbors, making them excellent for standard classification tasks. When networks grow massive, computing every single connection becomes computationally expensive. GraphSAGE solves this by sampling a fraction of the neighbors rather than processing the entire graph, allowing the AI to handle networks containing millions of nodes. But not all neighbors are equally important. Graph attention networks introduce a layer of discrimination. They learn to assign attention weights, prioritizing the most crucial connections and tuning out the irrelevant noise. Still, standard GNNs face the expressivity problem. Under tests like the Weiss-Feiler-Lehman algorithm, simpler models will look at two graph structures that are distinct in the real world and mathematically confuse them for being exactly the same. To fix this blind spot, engineers deploy graph isomorphism networks. By swapping out basic math operations for multi-layer perceptrons, GNNs can reliably distinguish between complex structural patterns. Finally, we reach graph transformers. This architecture allows any node to communicate with any other node across the entire network, mapping massive, long-range relationships without being limited to its local neighborhood. This progression provides enterprise engineers with a precise toolkit. Whether analyzing a local cluster or mapping a global supply chain, there is an architecture ready to handle that level of relational complexity. The end result of all this message passing and attention weighting is highly practical. Messy, real-world relationships are converted into dense mathematical vector embeddings that models can deeply analyze. This brings us to Anven, a model developed by Treecapital Technologies to run entirely within private, air-gapped clouds. It represents the transition from theoretical graph research to a secure, enterprise reasoning engine. Anven functions as an analytical bridge, interpreting the hidden dependencies within multi-layered data for executive decision makers. In global finance, this relational intelligence is critical. Anven traces hidden, suspicious transaction rings, detecting fraud that traditional, table-based algorithms often overlook. In the life sciences, this same underlying logic accelerates drug discovery. By mapping out atomic connections, the model accurately predicts complex molecular bindings, saving thousands of hours of laboratory trial and error. And in asset-heavy industries, mapping the dependencies between physical parts allows operators to optimize predictive maintenance and automate complex, interdependent workflows. By codifying the mathematical language of relationships, Anven interprets the specific connected logic of our global systems.